Welcome back to Calculus 1, and today we'll be talking about the Intermediate Value Theorem. So if you guys do not remember, last video we talked about the definition of continuity, and before you watch this, I preferred if you would watch that before going to here and talk about continuity. So the Intermediate Value Theorem, what does it talk about? The Intermediate Value Theorem talks about the it talks about the guarantee of a zero. And if you remember from Algebra 1 or Algebra 2, a zero is anything that crosses the x-axis. It's very rudimentary, but we'll leave it there. So it basically says that can we guarantee that a zero occurs at that point. So saying for a continuous function over the closed interval from a to b, and L is a real number between f of a and f of b, then there must be at least one value c, which is our zero, in the interval. Remember, it's open a to b such that f of c is equal to L. So f of c is equal to L could be any value. So let's see what the problem one is, and I feel it's best shown with an example. So show that this the equation x cubed minus 2x minus 5 equals 0 has at least one real solution between x equals 3 and x equals 2 and x equals 3. So what were interval b? Let's try to match it up with our theorem. So it's going to be 2 to 3. I feel like we could agree with that. And L, what is L? Well, we just want to know that we want it to be, as the theorem states, between f of a, which we'll call 2, right? Because the 2 corresponds to a up here. We'll do f of 2. And must be less than or equal to a real number between f of a and f of b, so which is L, less than or equal to f of 3, because that's going to line up with b. And then we will do, so if this holds, then there must be at least one value of c in the interval, the open interval from a to b, such that some number c is equal to L, okay? So let's try it out. So what is f of 2? Well, let's just say let f of c equals 0, and we said that our f of c is going to be equal to L. So we know that f of 2 is less than or equal to 0, is less than or equal to f of 3. We need to see if this is true or not by plugging in. So now we have that f of c, because if you plug in f of c here, our f of c is going to have to be c cubed minus 2c minus 5. So let's see, what is f of 2? So we have 2 cubed, right, which is 8, minus 2 times 2, which is 4, then minus 5, and then you'll have 8 minus 4 is 4, minus 5 is negative 1. So far, so good. And then what about our f of 3, or f of 3? Well, 3 cubed is 27, and then minus 3 times 2 is 6, and then minus 5. So we're going to get 21 minus 5 is 16. Does this hold? So yes, this does hold. So we can and also I forgot to mention this in the beginning, that all polynomial is continuous over its entire domain, and this is a polynomial, so we don't have to worry about continuity here. So our proof statement could be, we can guarantee at least 1 0 over the interval, open interval from 2 to 3. And that will be our proof statement. Okay? Moving on to number 2. Let f of x equals sine of x on the interval from 0 to pi. Prove that there exists some c such that f of c is equal to a half. Okay. So let's start here. we already have our A and B laid out neatly. So this is going to be our A, and this is going to be our B. So we're going to do f of A is less than or equal to f of C is less than or equal to f of B. Okay? So f of A will be f of 0 and less than or equal to f of C is less than or equal to, so what we actually said down up here, the problem gives us f of C. It's going to be a half. So it's going to be a half, and then that, and then f of B, which is going to be f of pi. So what's sine of 0? Well, sine of 0 is 0. And then f of pi, which is going to be sine of pi, is also going to be 0. All right, we're in a little bit of a predicament. 0 less than 1/2. So this part is correct. So yes. But is this half correct? No. And also, this trigonometric function right here, I keep forgetting to mention it, is continuous over 0 to pi. Okay? And it's actually continuous everywhere. Okay? So since this inequality doesn't work, so we can't guarantee at least one value of C for which f of C is equal to half. Okay? So let's move on. So show that x to the fifth minus x cubed plus x minus 2 has at least one root in each of the intervals. So we'll start, this is actually two problems in one. So I'll start with this one. So this is going to be our A, and this is going to be our B. Is this continuous everywhere? Well, yes it is, because it is a polynomial. Okay? So, well, let's figure it out first. So it's going to be f of A and f of C. And remember, we want it to be a 0. And in order for it to be a 0, f of C must be equal to 0. Okay? So we're going to have f of A. So f of A, we'd find A to be 0 here. Less than or equal to f of C, which is going to be 0. And then B is going to be f of 1. So let's plug this in. I actually think that we should also label what intervals we're using for the sake of cleanliness. So we'll say this is 0, comma 1 here. There. Okay, and then we'll plug in. So f of 0, so of 0 to the fifth, minus 0 cubed plus 0 minus 2 is just going to equal minus 2. So f of 0 is minus 2, 0, and then let's evaluate f of 1. So 1 to the fifth is 1 to the fifth, then minus 1 cubed plus 1 minus 2. This can be equal to 0, and this is going to be minus 1. So is this part of the inequality correct? Yes. But is this part of the inequality correct? No. So we cannot, so our first problem statement is we can't guarantee a value where f of C equals 0 over the interval 0 to 1 open. Okay? Now what about 1, comma 2? So well, we'll have our A here and our B here, just following the formatting of the theorem. And then we'll do the exact same thing. So, but we're still keeping f of C is equal to 0 because you want to see if it's a 0 or not. So it'll be f of A Then f of c would go right here, but since we know f of c is equal to 0, we'll put 0 here. And then f of b here. And then f of a is going to be f of 1, and we evaluated f of 1 here. It's going to be negative 1, so we can just copy that over. It's less than 0, and then f of b, which is b is equal to 2. Okay? And then we'll plug in f of 1, so be negative 1 less than or equal to 0. And now let's try to do f of 2. So we'll 2 to the 5th minus 2 cubed plus 2 minus 2. So 2 to the 5th is 32 minus 2 cubed, which is 8. And then 2 minus 2 is 0. And that's going to equal 24. Okay, so let's see. Is less than or equal to 24. And negative 1 is less than or equal to 0. And then 0 is less than or equal to 24. Okay? So we can say we can guarantee a value. We can guarantee a root over the interval 1, 2. And that is a good problem. And that's a good proof statement. All right. Is ln of x continuous over here? Yes, but this is not a polynomial, so you have to tread very, very carefully on when is it continuous or not. Well, it's not defined for, x is less than or equal to 0. But our interval of interest is 1 to 10, and that is not included in here. So we're okay continuity-wise. So prove that there exists a point that c is part, or this is the epsilon, it's the mathematical symbol for within, such that f of c equals 2. Okay, so let's do the same thing we've been doing. So f of 1, before I jump the gun, f of a is less than or equal to f of c is less than or equal to f of b. So f of a, right, we'll just format it. This is going to be your a, this is going to be your b. So f of a is going to be 1 is less than or equal to, well, we said f of c is going to be 2 over here. And then f of b is going to be f of 10. Okay, so what do we know about ln of 1? ln of 1 is 0. Then f of 10 is just ln of 10. Now, ln of 10 is going to need a little approximating. So we say we can guarantee a c such that f of c equals 2 over the interval it's not closed, it's open, 1 to 10. Okay, so consider f of x is equal to x to the 7th plus x minus 1 on the closed interval 0 to 1. Use the intermediate value theorem to show that f of x equals 0 has at least one solution in that interval. Okay, so let's set up the same usual thing, f of a less than or equal to f of c, and we said we wanted it to be a 0, so f of c is going to be equal to 0. So, and then we'll add f of b here. Then we'll assign using the template version of our theorem. So it's going to be b, and this is going to be a. So f of 0 is less than or equal to 0. So less than or equal to f of 1. So f of 0, well, 0 to the 7th is 0, plus 0 minus 1 is negative 1. So negative 1 is less than or equal to 0. So less than or equal to f of 1. So it's going to be 1 to the 7th, which is 1, plus 1 minus 1 is going to be 1. And 0 is definitely in between negative 1 and 1. So here, again, we can say we can guarantee a c such that f of c is equal to, we said, 0 over 0 to 1. All right. I hope this helped, and I'll see you all next week.